Hi, I am Michele Ciampi and I'm going to talk about updatable blockchains. This is a joint work with Nikos, Karayannidis, Aggelos, Kiayias, and Dionysis, Zindros. So software changes, we know that very well, and the software can change for many reasons. For example, if we want to have better performance, we want to add new features, and to fix some security issues. And if we think about how nowadays software system work, we know that to have an update, it's kind of pretty simple, right? So, for example, we have our word processor, and when there is a new release, we just download the new release, we install it, and we are happy. Blockchain systems are very different from that, as they are distributed systems. So we need to deal with this kind of system in a different manner when it comes for updates. And what we do in this work is providing what is a secure update for blockchain and what kind of properties we should ensure, and also show how to construct a blockchain system that tolerates updates. At a high level, a blockchain system can be seen in this way as a sequence of blocks, where the sequence starts from a block that we call the Genesis block. This Genesis block usually comes from a trusted party, and it's generated at time t0. And we know that if an assumption holds, for example, if the majority of the hashing power of the parties that are running the system is above some threshold, we will have two main properties, which are consistency and liveness. Consistency says that the history of the blockchain is preserved. So more precisely, it says that the honest parties will agree on a prefix of the blockchain at any time. And liveness says that new blocks will be added to the chain as time advances. Without loss of generality here, when we talk about an assumption A, we will just say that A holds if the number of malicious parties is below some threshold T. And this T parameter can change depending on the blockchain. So there are many ways to update a blockchain. And for example, one of the simplest ways to think about changing the structure of the block. So for example, increasing the size of the blocks. Or we can have something completely different and less trivial, like changing the consensus rules, for example, or changing the reward scheme. And it doesn't matter what kind of updates we do, if it's a very simple update or a very or a difficult and a more complicated update, we want to do it in a secure way. But what does it mean, security, in the case of blockchain, and more precisely in the case of updates for blockchain? So, as a first contribution, we provide exactly this definition. So we define what is an updatable blockchain, and for us, an updatable blockchain is a blockchain B that enjoys the standard properties of consistency and liveness, with the additional property of updatability, where updatability says that if we have many users, many parties that are running this blockchain, these parties can at some point decide to update this blockchain. So B tolerates another command, which is update, and if enough parties want to update to some blockchain B2, where B2 can be seen as the blockchain B, but with some improved feature, then if the parties that request this kind of updates are such that the assumption that underlines B2 hold, we have that after some time, that we call D, those parties will be running the blockchain B2, so they will be generating blocks according to the blockchain B2, but this new chain will have as a prefix the blocks that were generated at time t7, where the time t7 is the time where enough, let's say, update commands were received from the users that were running the blockchain. So, to summarize, what we want from an updatable blockchain is that it's secure under the standard definition of what a secure blockchain is, but in addition we want to allow the parties to say, okay, I want to update now, I want to activate a new code, which is B2 in this case, and we know that if enough honest parties want to do the update and there is an agreement on how the blockchain should be updated, after a period of time that we denote with T, these users should be running V2, where we have consistency aliveness, but with the additional requirement that the prefix of these blocks contains the history of the old chain, that is B in this case. Now that we have a definition of what is a secure updatable blockchain, let's see how we construct it. In this work, we want to provide a compiler that, starting from a blockchain, it turns this blockchain into an updatable blockchain. We will provide two compilers, but we first observe that it's kind of easy to realize an updatable blockchain if we can rely on a trusted party. So in the sense that, let's say that we have a standard blockchain, B1, the users are running it, and now sufficiently many users want to update to B2. And those users can communicate this to the trusted party. And now, if enough parties wanted to update and there is an agreement, the trusted party can timestamp the history of B, and then from that point on, the parties can start running the new rules of the blockchain B2, where each block is generated consistently with what the history of B was. But the point is that we don't want to rely on a trusted party, we would like to have a decentralized software updates. And for that we propose actually two compilers. The first compiler is very simple, but it allows for very few updates, in the sense that we allow to go from the blockchain B1 to the blockchain B2, where the only difference between B1 and B2 is in the block structure. For example, B2 has larger size in the block. And what we show is that in this case, it's actually pretty easy to realize an updatable blockchain, because the updatable blockchain will be just B1 that is used to reach an agreement on an index of a block. And then, after that this block is generated, the parties will start running the blockchain B2 instead of B1 to extend this block. So this approach is pretty intuitive, and we actually formally prove that if this index is chosen carefully and accordingly to the liveness and the consistency parameters of B1 and B2, then the update is secure, in the sense that the history of B1 is preserved and you have consistency aliveness. The other nice thing about this approach is that the update is very fast and the throughput does not decrease during the update. And also, if a party is offline during the update, there is no problem here, because we can guarantee that even if you're a party that you were offline during the update, at some point you will catch up and you will be using the updated version of the blockchain. The second approach that we propose is different, and it allows for a larger class of updates, but it requires B1 and B2 to be Genesis compatible. So that's something that we define, and we define Genesis compatibility as follows. So B1 and B2 are Genesis compatible if there is an algorithm of Genesis that takes as input a block from B1 and turns this block into a valid Genesis block for B2. Okay, so now, under the assumption that B1 and B2 are Genesis compatible, let's see how we transform B1 into an updatable blockchain. So the updatable blockchain will behave exactly as B1, but the parties will use B1 to reach an agreement on an index J, on a block index. Moreover, we assume that the parties at this point have also agreed on what is the new blockchain that they want to run, on what are the features of the new blockchain that they want to run compared to B1. And after that, the jth block has become stable, which means once that B1 is the same in the view of all honest parties, these honest parties then can take the jth block, generate a Genesis block for B2, and can start extending this Genesis block using the rules of B2. And at this point, we have that each party, I'm talking about a party that decided to update, will keep the history of B1 until time t7, and will start working extending this Genesis block using the rules of B2. So the property of liveness and consistency are preserved because the assumption that underlies B2 holds. That's what we are assuming. Moreover, because of the Genesis compatibility property, B2 is a good Genesis block for B2, and so we are fine. And the updatability property also requires that the history of B is preserved, and that's still true because all the honest parties that decided to update will keep an history of B1 and will accept transactions in B2 only if they are consistent with the history of B1. So there is still a problem with this approach, and the problem is that it requires more assumptions than I said. And the reason is the following. So in this case, the Genesis block of B2 does not come from a trusted party. It is the output of protocol. This means that potentially the adversary might see this block before the honest parties do. And in addition, this block might be adversarially biased. If B2 is a blockchain protocol that is proven secure in isolation, which means that it's proven secure under the assumption that the trusted party issues the Genesis block, and then both malicious parties and honest parties can see the Genesis block at exactly the same time. But unfortunately, that's not true in our case, but that's not true in many other scenarios where this block comes from, for example, an MPC computation. So what I'm saying here is that if you want to use our protocol, our compiler, you need to use a B2 that is resilient against these kind of adversarial behaviors with respect to the Genesis block. So the nice thing about this protocol is that it's generic. It allows for a large class of updates, but it requires a stronger security notion from B2. And also, the other thing is that the transaction throughput decreases during the update for the following reason. So once that the Genesis block of B2 has been created, we want the honest parties to just run the blockchain protocol B2. We don't want those parties to run B1. So the idea is that after T7 plus D, each honest party will be running just B2, not B1 anymore. And this means that all the transactions that are in the blocks that appear after T7 will not be valid anymore. This means that during the update, the transaction throughput will decrease significantly. And even if this is a bounded time that we can estimate, it's still a drawback. And there is another point that we should now mention, which is what about the security for the parties that were offline during the update. The problem is that if the honest parties abandon B1 after time t7 plus d, this means that an adversary could potentially do forks, could completely compromise B1 for parties that were not aware, were not online during the update. So more precisely, if a party was offline at time t2 and comes online at time t7 plus d plus some delta, this party might now see a chain that has been compromised, because as the honest parties leave B1, it might be that the assumption that underlies B1 does not hold anymore. And so we cannot give any guarantee with respect to the view of the parties that were offline during the update. But we note that we could require the parties to not leave B1 and run in parallel B1 and B2 for as much time as you want. And the nice thing is that this is almost for free in many cases. For example, in the case of proof of stake, it's not that costly to run two blockchains in parallel. And in the case of proof of work, well, in that case, we can use other techniques, like for example, the 2-for-1 mining. And this will make this process very light. So, in conclusion, in this work, we have provided the first definition of updatable blockchains, and we have provided two compilers, where each of these compilers takes as input a blockchain and outputs a blockchain that tolerates updates. So the first compiler is very simple. It just requires to run the previous blockchain and at some point to switch to a new blockchain protocol. It just requires the parties to reach an agreement on when to do this switch. It doesn't decrease the throughput during the update, but the problem is that it allows for just few updates, or to be more precise, for a small class of updates. The second protocol is more involved and might require to run multiple blockchains in a concurrent way in order to be secure also in the view of the parties that were not online during the update process. But on the positive side, it allows for a larger class of updates in the case that the updated blockchain has some features that we described earlier. And with that, I am concluding my presentation. Thank you very much.